just like we explored sample proportions and their distributions, we can do the same with sample means. And in a sense, there will be a lot of similarity, but there will also be some differences. The idea is we have some population. And we're talking about quantitative data because we want to take means. But we assume that we know mu, and possibly we know the standard deviation. So we are literally talking about population parameters, just as we did in the previous unit. So descriptive statistics, dig back there, we know how to find these from the population, but we take random samples of a certain size. And we'll put a note that we mean sufficiently large. So the sufficiently large idea is because in order to properly be able to use the power of probability, we need to be able to generate a sampling distribution using sufficiently large sample sizes. This is often one of the cardinal sins committed by studies in statistics and in other fields that end up being not found fraudulent but faulty. So when we do this, so we're gonna fix this size n, and we're gonna take repeated random samples from each sample. So here's a collection of samples, just for the sake of illustration. From each one, we get a sample mean. And the distribution of sample means is going to tell us the probability distribution of this random sample, which we denote as a capital X with a bar on top. And in the long run, this distribution is determined or approximated by a histogram of these random sample means. Now, you may be wondering, if we're taking sample means, this is relatively easy in terms of our random outcomes, because each random outcome is its own random variable, if we can think about it as a specific instance of a random variable, and we just divide by how many we have. So we're actually just adding up all these random outcomes and dividing by how many we have. So maybe something nice happens with sample means. What can we say about their distributions? Well, when we know sigma, and so we actually are going to have to differentiate between two different cases. So case one. So the population standard deviation is known. Then we have the theorem that says that given sufficiently large random samples of size n, then the sample mean as a random variable is normally distributed with a mean, which I'm going to denote as mu of x bar, which is equal to the original mean. So the mean of the distribution. In other words, if you have your histogram of the random sample means, so this is the histogram of x bar, then its peak, its center, is going to be located at the population mean, which is what we want. This is cool. And its standard deviation of the sample mean is the original standard deviation divided by the square root of the sample size. So why is this important? So first of all, again, we have the power of the normal distributions. So we can find all sorts of interesting information about the probabilities associated with how likely a sample mean is, what's the percentile of the sample mean distribution, etc. And depending on the sample size, then we'll get an either very wide distribution or a not so wide distribution. So very importantly, for the sake of making sense of this computationally, right, let's take random samples of different sizes from a normal distribution with a mean of 100 and a standard deviation of 15. So I'm using the same parameters as IQ, but no IQ. No more. Anyway, so in the first, so scenario 1, or scenario A, I guess, if we let n be 10, so we're taking repeated samples of size n. So 10 people from this distribution, 10 subjects. And we observe these random sample means, then we'll find that the sampling distribution, so the mean will always be 100, okay? So the sampling distribution, its center will be 100, but the standard deviation will be 15 divided by the square root of 10, which is roughly 4.74. So already this has much lower spread than, much lower variation than the original distribution. So if you will, here's the original distribution maybe. And here is the distribution of the sample mean. So it's got a lower, oh boy, got a lower variance, lower standard deviation, but they're centered in the same spot. So here's mu. If we keep increasing the sample size, so let's say n equals 50, then again, the only real difference will be that our spread is going to be even smaller. So we now divide 15 by the square root of 50, and that's approximately 2.12. So in keeping with this idea of we're going to place the original population distribution, then our sampling distribution just gets even more, oh, this is terrible, I'm so sorry, has an even smaller spread than before. No, this is really bad, hang on. But they have the same peak, again, always. The idea here is that the larger the sample sizes we take, the lower the variation for the sampling distribution of the sample mean. And in fact, this was also true for sample proportions. And it's a key concept when we're talking about sampling distributions. So in sampling, large sample sizes reduce variation. And variation can have different interpretations. It could mean risk. It could mean error. So if we want a tighter bound on our observations, and we want to be more and more sure of where we are relative to the mean, the original mean, then we should take larger sample sizes. All right, so that's the first case. We know how to work with normal distributions, so we'll leave it at that. But case 2, what if we don't know the population standard deviation? Well, this is not going to give us the same sampling distribution. And another thing to note here is also what if n is not sufficiently large? And now is a good time to define this. When we say sufficiently large, we mean n is greater than or equal to 30. So sufficiently large means greater than or equal to 30. Less than that means it's not sufficiently large. Then our sample mean has something that we would call a student t-distribution with degrees of freedom, which we often call df, n minus 1. So you have a sample of size 10, the degrees of freedom is 9. Okay, and we'll talk about this in a future video, but the student t-distributions are very similar to normal distributions in that they have this characteristic bell shape, but they have what we call fatter tails. So it has a mean of 0, but the standard deviation is larger than the standard normal distribution. And we'll talk about this in more detail in a later video.